Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We are almost near the end of this course, and in this particular lecture I am going to talk about characterization of porous media. In particular, how to measure, for example, porosity, how to measure the internal surface area of a porous matrix, because these are all very important. If one wants to use porous media as a catalyst, then surface area is extremely important. Basically, because of this advantage of high surface area, a porous medium is chosen as a catalyst. I mean, catalyst material is deposited on a porous media just for this reason, so that you can utilize the high surface area. And similarly, what is how to calculate the pore volume? If it is oil and water trapped in a reservoir in subsurface, then how much is trapped? So that depends on what is the pore volume. Similarly, what is the transport? I mean, how well this fluid can be transported through these porous media? What kind of pore size distribution it has? So these are very important parameters, and one needs to characterize the porous media with respect to these parameters. So this is something which we are going to discuss in this lecture. So we are going to talk about various characterization methods to determine the porosity, pore size, internal surface area, permeability. First thing is porosity measurements. See, porosity measurements, porosity is, we started with definition of porosity. It is basically the void volume divided by the total volume. In 1 meter cube of total volume of this porous media, if out of 1 meter cube, if we see 0.2 meter cube is the void area and 0.8 meter cube is the solid area, then 0.2 divided by 1, so porosity would be 0.2. So now this porosity can be measured by different methods, as pointed out here. The first one described here is optical method, where one can observe the porous medium under a microscope, observe the cross section under the microscope and estimate the void content. That means, if you take a cross section, if you take a slice of the porous medium and then put it under a microscope, then you will see some parts are occupied by the solid and then some part as void space. So now one can calculate, one can find out which part of the area that we are looking at, which part is solid and which part is void, and from there one can do this calculation to find out what is the porosity, right. So that would be probably applicable per unit depth perpendicular to the image that is taken. So that porosity can vary. I mean, one can take different slices at different axial positions and can find out what is the porosity variation. So the one way to look at it is obviously the direct method, which is optical method. Observe which part is void and which part is solid. Okay. The second method is known as imbibition method. Imbibition method is immersing perfectly wetting fluid under vacuum for a sufficiently long time, and the weights before and after imbibition are measured. That means, when you, first of all, you must note couple of things here. One is that there has to be a vacuum. So this is under vacuum, and then it has to be a perfectly wetting fluid. So under vacuum means inside whatever, suppose inside the porous medium there is some air in it, there is some volatile matter in it. So all those things under vacuum, they will come out. So there is nothing inside the void, and now you are dipping it, immersing it in a perfectly wetting fluid. Wetting fluid means wetting fluid can penetrate every nook and cranny of this porous media, everywhere. Okay. Had it been a non-wetting fluid, then there comes this issue of capillary pressure and what pressure you are imposing. Some pores will be penetrated, some not, but wetting fluid, it does not have, there is no such problem. So wetting fluid will penetrate. Now you note the weight before and after imbibition. So That means before putting water in this, it has certain weight, and after water fills all the pore, you measure the weight. So, difference between these two weights, that gives the amount of water that has gone into this porous medium. So, you know initial weight, that is the weight of the solid matrix. You know how much is from this difference, you know how much of weight of water has gone into this porous matrix, and the final weight is the sum of these two weights. So, now how much water has gone into this porous matrix divided by the sum or divided by the final weight, which is water plus the original solid weight. So, that gives you the porosity. So, this is one very simple way one can get the porosity. Of course, the first one, the optical method, gives you a local porosity, whereas this imbibition method, that gives you the porosity for this entire porous matrix that you are looking at. Suppose you are looking at a core, that then entire core that you will get one average porosity of the core. It is not a local porosity of any position. Or one can do something called a density method, where density method says that it is from the comparison of the density of porous sample and the bulk density of solid. That means you measure the density of the porous matrix. Density means density is kg per meter cube unit. That means what is the weight of that porous matrix divided by what is the volume of this porous matrix. So, one can find out what is the volume of the porous matrix, making measurements, and then one can find out what is the weight of that porous matrix. So, then you find out what is the density of this porous matrix, and at the same time you know this porous matrix is made of some material, and we already, if you crush it to the finest of this size, you will get to something called a bulk density, or generally this bulk density of various known materials are already listed. So, you have a priori knowledge of what is the bulk density. So, by comparison of these two densities, one can get the this density, or one can get the porosity of that sample. And the last 2 points that we have here, one is gas expansion porosimeter and another is mercury injection method. These two we are going to discuss in detail. So, this is the description of a gas expansion porosimeter. So, what we see here is there is a cell sample, there is this cell sample, there is a cell with sample. So, there is one cell here, and this cell is containing the porous solid for which we want to measure the porosity. There is this sample, and then we know the volume of this cell. We know the volume of this cell, and first what you do is you create vacuum and clear this. There is one reference cell. So, you clear this reference cell, you take out all the gas out from this. So, there exists vacuum. You close this valve, and then you close, there was vacuum and there is this sample, and then you open this valve so that the gas goes in here. So, gas goes in here, after some gas goes in here, you will see this valve is closed, this valve is closed. So, there is in this transducer there is a pressure reading. So, you note down what is this pressure, because and then you close this valve, you note down what is this pressure, and the pressure is P1, let us say. So, at this time I have solid sample present. So, let us say this is the solid sample, and there is this gas present, and the gas is at a pressure P1. Then what you do is, after this entire thing equilibrates, then you open the this valve is closed. Now, you open this valve so that some gas can flow from this one to the reference volume. So, as soon as because this was originally in vacuum, so there will be flow from this pressure P1 to vacuum. So, there will be flow of gas to this reference volume, and then there would be an equilibration. So, after equilibration, let us say the pressure noted by this transducer is P2. Okay. So, in that case, we can do some quick calculation here. We can make use of something called Boyle's law. So, initially, let us say we have Vc as the sample of as the volume of empty sample chamber. So, the volume of this sample chamber, this is called sample chamber or sample cell. Here, let us say the volume is Vc, and Vs is the solid volume that you have given, which is called sample volume, whose porosity you want to measure. So, this is called Vs. So, Vc minus Vs, Vc is the volume of this sample cell, and Vs is the volume of the sample. So, Vc minus Vs gives the volume of the gas that is occupying here, and that multiplied by P1. So, P1 V1, V is the volume of the gas occupied in this sample cell. So, that P1 V and that same gas, now after equilibration, after allowing the flow from this cell to the reference cell, so at that time the pressure became P2. So, the same gas, earlier it was in P1 V1, now it has to be P2 V2. So, what is that? So, that would be P2 into, now we have this volume remains same, Vc minus Vs. So, some gas will be in this and some gas would be in this chamber which was earlier in vacuum. So, if the volume of this reference cell is Vf, so P1 V1 would be P2 into Vf, some is here, some of the gas is here and the rest of the gas is remaining there, but both of them have equilibrated to a pressure P2. So, this is the relation Boyle's according to Boyle's law, P1 V1 has to be equal to P2 V2. That means, after expansion P1 V1 will remain same. So, if you now use this equation, this will take you to, if you simplify it, then Vs, the sample volume, will be given by Vc plus this quantity. So, now Vc is already known to you, that is your creation, you have created the sample cell. So, you know the volume of the sample cell. Vf is the volume of the reference cell. So, that also is your creation, you know that, and you have made this measurement of P1 and P2. So, you know what is P1, what is P2. So, with this you can find out what is the Vs, volume of the sample. So, now what is the volume of the sample? The sample volume Vs estimated here is volume in sample chamber from which gas is excluded. So, that means, think of it, this is a porous material whose volume you are trying to measure. So, what is this volume? So gas had gone into, when you did the equilibration, gas has gone into this cell, gas has gone into this porous matrix, and then when this pressure is reduced, because there is flow from gas from this side to this side, automatically some of the gas came out from the pores. So, what is Vs? Vs is basically the volume from which the gas is excluded, that means volume of the solid, true solid volume, not the porous medium volume, the true solid volume where the gas could not penetrate, because the void space within the porous medium, that is anyway accessible by the gas. So, that is basically the gas volume included. So, now you get the volume of the solid. Now, if you have the information of what is the total volume of the matrix and now you have the information of what is the solid volume, then total minus the solid volume is the void volume. So, by this way you can find out what is the porosity. Now, here the type of gas that is used, see, essentially Vs is the 3-dimensional space in porous media that is inaccessible to gas. We understood that. Helium, because of small size, can penetrate even to the closed pores. So, it is very important that you use a gas whose size is very small. Okay. So, that is I mean it is not it should not be large molecules, because you want it to have the high mean free path, you want to have the good diffusivity. So, all these things. So, helium is the choice here. So, helium is inert and most ideal gas to follow Boyle's law. So, helium is a good choice here, and you want, even if it is a closed pore in the sense it starts with the pore it is like this. So, helium can enter, I mean, but helium cannot leave. So, still, since it has a high mean free path, helium can enter and gradually occupy this space. So, this is more or less the structure by which this gas porosimetry is conducted. The next one is mercury porosimetry. Here, intrusion of a non-wetting liquid or mercury at high pressure into porous media and determine external pressure needed to force the liquid into a pore against the opposing force of liquid surface tension. You must recall one thing here is that this mercury would be considered here as a non-wetting liquid, and you know, when you want to push a non-wetting liquid inside a porous medium, one has to overcome, one has to provide some extra pressure because it does not get a favorable contact angle. So, as you increase the pressure, you will see some pores penetrating. This is unlike the case of imbibition method we discussed. You put it in a perfectly waiting fluid and waiting fluid will penetrate every nook and cranny of that porous medium. But when it comes to mercury, which is considered here as a non-waiting liquid, it will not enter into the porous medium that easily. I mean, it has that problem of contact angle, adverse contact angle. So, the way you must look at this is that it has to overcome something called the capillary pressure. You must recall by now that we had a discussion that if there is a cylindrical pore, and if non-waiting fluid is pushed into this. So, originally let us say you have a vacuum and you want to push this non-waiting fluid. So, let us say you have air at very low pressure on the other side and then you want mercury to go in there. So, in this case you will see that the liquid pressure is equal to the gas pressure, which is, if you consider this to be vacuum, this would be close to 0, minus 4 sigma cos theta divided by the diameter of the pore. This you must recall that we have, you remember, if there is a surface tension force, then this is you must recall that there would be a meniscus like this, and then this meniscus will have this would be the contact angle. So, contact angle will be this much, greater than 90 degree, and as the fluid penetrates, and you have the surface tension force acting is sigma into pi into dp, that is basically 2 pi r, the perimeter multiplied by cos theta. So, that is the force which is acting over the area of pi dp square by 4. So, this gives me the pressure, the additional pressure that has to be provided to the liquid phase here. Okay. So, now this is basically here this cos theta would be in this case negative. So, this will become positive. So, PL would be higher than PG. So, you have to provide this additional pressure, then only the mercury will penetrate. So, you can see here that sigma, theta, etc., these are defined here, the numbers are given. So, if you put these numbers, you can see the pore diameter will be given as 1470 kilopascal into micrometer divided by PL, where PL is the liquid side pressure. So, what it says is that as you increase the pressure, suppose I want mercury to penetrate into the pore and I have pores of different dimensions, some are small, some are large. So, then mercury will penetrate. Moment I increase the pressure in the mercury phase, I will see mercury will penetrate in the largest pore, because this as the pressure increases. So, here you can see as PL increases, pores of smaller dp can be included. So, for the lowest pressure, the largest dp would be included, and then as PL increases, you will see that smaller and smaller dp will be penetrated. Okay. So, essentially if we try to plot this here, it is the volume penetrated as a function of the pressure. Here we see that the pressure, as the pressure increases, we will see that the more and more fluid will be penetrated. So, more and more mercury would be penetrating into the porous medium, and every pressure here in megapascal corresponds to some pressure of corresponds to some dp. So, some dp, this pore radius is basically what? Pore radius is basically dp by 2, and we have already seen that dp is proportional to 1 by PL. So, as the pressure increases, you can see that dp by 2 decreases. So, it is basically these two axes, they are synonymous. In this case, you have the pressure is increasing from 0 to 100 to 200 to 300 megapascal, 400 megapascal. Corresponding pore radius Okay, just in the last slide we had a discussion. In the last slide we showed that corresponding to this, this is changing to 2000 angstrom, 100 angstrom, 50 angstrom, like this. So pore radius is decreasing. So now as the pressure increases, smaller pores are getting penetrated. Now you can see here there is a trend. First of all, this is going like this and then it is reaching a constant value. So that means constant means you are increasing the pressure but no change in volume. So nothing is being penetrated, whatever was there, status quo is maintained. Then beyond this threshold pressure, I see again the volume started changing. So from this point some invasion starts. So so I can see, now I tally these and I can see that there is some number of pores of this particular dimension. This particular pore radius of so many angstrom, this particular dimension, there are few pores, because I can see now in the porous medium the volume of mercury intruded is, they start increasing. Again here it starts flattening. That means, so from this size to this size there was continuously some pores were invaded, but from this size to this size there was no invasion because volume does not change but pressure continuously is increased. But then again from this point again I see increase. So again from this point onwards there would be some pores in that matrix which are of this dimension. So there is no pore present there of this pore dimension. There are some pores present in this dimension, again no pore in this dimension. So from this you can get a picture what are the pores that are present in this porous media. They belong to what size ranges. I mean this to this. So these are the pores that are present in the system by looking at this curve from mercury. That this curve is generated from mercury intrusion porosimetry. Of course, when you come back on the reverse, there would be a huge hysteresis, and these hysteresis we are familiar with because you remember oil water case. Then when oil entered, it entered in one way, but when you are retracting, when you are taking out oil, so from the other side then air is entering, so then that means from the other side it will happen from the other side. But the mercury, which is a non-weighting fluid, it will enter through the largest. So if you have a varying cross section, mercury will enter through the larger end of the pore, whereas the pore where the cross sectional area is larger, whereas it will enter when it leaves, that time the gas will enter from the other end where the cross sectional area is smaller. Okay, because this non-weighting fluid is, so this we have studied in case of oil and water and this hysteresis. We talked about drainage and imbibition and we had this capillary hysteresis. So the same thing will happen on the, but we are not bothered with let us focus only on this part, and one can find out what all pore sizes are present in the porous matrix and what all sizes are not present. So with this understanding, let us now look at when the radius, suppose if I want to generate a pore size distribution, how it looks, I can give it here. When the radius of a cylindrical pore is changed from r to r minus dr, the corresponding decremental change in the pore volume V is given by dV, which is this quantity minus 2n pi rl dr. Okay, because this change in volume, it would be it is the corresponding decremental change in the pore volume would be given by this quantity, where n is the number of pores with radius r and length l. So there are n number of pores of radius r and length l. So corresponding change from r to r minus dr is this quantity. So now when the pore radius into which intrusion occurs changes from r to r minus dr, the corresponding volume change dV, that would be equal to minus capital D subscript V as a function of r dr, where this D subscript V as a function of r is pore size distribution in terms of volume, pore size distribution function defined as pore volume per unit interval of pore radius around r. Okay, so this is defined as pore volume per unit interval of pore radius around r. So now we already know that the pressure, we have already defined this expression. So, if that is so, we know that the P into R, if sigma and theta, these are all system properties. So, P into R is equal to constant. So, one can write d of V is equal to d of V is, so since P into R is equal to constant, so one can write d of PR would be equal to 0, and d of PR equal to 0 means P dr plus R dp equal to 0. So, P dr plus R dp equal to 0, what that means is that one can write this dV is equal to minus dV R dr. Instead of this dr, we can use this dr. So, this dr would be here, this dr would be minus R by P dP. So, this is minus R by P dP. So, that is brought here. So, dV is equal to dV into R, and this minus and minus became plus R by P dP. So, then this dV can be written as P by R dV dP. Okay. So, now one can plot this dV as a function of R, dV as a function of R, and one can generate a curve like this. It's this P for a particular R, you know what is P and what is corresponding dV dP. So, one can generate this curve based on the mercury porosimetry information. So, what essentially this gives? This gives, let us say I am talking about a pore radius of, let us say 0.01 micrometer. So, 0.01 micrometer, this corresponds to this value of dV, whereas if I am looking at 0.001 micrometer, that is giving dV as this. So, dV is, once again, the dV is the volume pore size distribution function, which is basically the pore volume per unit interval of pore radius around R. So, what that means is for this particular R, this dV gives me pore volume per unit interval of pore radius around R. So, this is basically, so this gives me, so if this is highest here, that means at this particular pore radius you have the maximum number of pores, and the pore volume that is having a pore radius of this, around this you have unit interval. So, this basically this particular interval here, that is having this much of pore volume. Similarly, you can have this interval is having this much of pore volume. So, here essentially by looking at this plot, you can say, okay, I can see 0.01 micrometer size pore is mostly present, and from that you can find out, okay, I would say 75% of the pores are of 0.01 micrometer and probably 5% of the pores are of this. So, one can get this kind of understanding of the porous medium by performing this analysis. So, you can, so this is as far as the mercury porosimetry is concerned, and I want to stop this session here, stop this particular lecture here, and I will talk briefly about other characterizations methods which are not that I mean other characterization methods we will touch upon. Those are not exactly for the porosity or pore size distribution, but for other purposes we can use those characterization method that I am going to talk about in my next lecture. That is all. Thank you very much.